Hello, my name is Maxim Goryachev. I represent the dark matter and quantum metrology group at the University of Western Australia, and we are a part of the Center of Excellence for Dark Matter and another one for engineered quantum systems. In this work, I want to talk about searching for new physics with photons and phonons. And in particular, this is the outline of my talk. In particular, we will discuss wave-like dark matter and high-frequency gravitational waves and how to detect them with photons or microwave cavities in particular, and phonons or acoustic cavities from the other side. So I start with microwave cavities. And the dark matter candidate we are going to discuss today is called axion. Axions are well known. They are excellent candidates for dark matter because they also solve other problems like the strong CP problem and the matter-antimatter asymmetry problem as well. And they naturally come from the theory. The answer whether they can be detected in experiments was answered by Sikivie. And here I show a classical Sikivie haloscope, which relies on this interaction between axion field A and electromagnetism in the form of E and B fields, and G, A, gamma, gamma is the interaction strength, which are basically being excluded by many of these experiments. So this classical experiment looks like this. So we have very strong magnetic field, and virtual photons from this field interact with axions via this interaction, creating real photons which are collected by a cavity and then amplified and detected. The result would look like this. So we have a small blip at a certain frequency which corresponds to mass ma of the axion, and the power of this blip is tiny. Since we don't know the exact mass, we don't know the frequency, so we have to tune this cavity. They are always narrow bands. So tunability is a must in these experiments. So the scan rate is the main feature of this experiment. So how fast we can keep going in frequency space or mass space in time. And this scan rate, we need to increase it, and it depends on the nature, this green part. Then it depends on the experiments, signal to noise ratio, temperatures, magnetic field, and also depends on the cavity. So over past decade, people keep improving these terms in order to increase the scan rates. If we knew the exact mass of an axion, we can detect it tomorrow. But that's not the problem if we would know the mass, but we don't. So unfortunately for us, the scan rate drops very quickly with the frequency of mass, so that we lose our sensitivity towards higher masses. So this was a challenge for us, and our experiment is called ORGAN, or Oscillating Resonance Group Axion Experiment. We run it here at UWA, and we are in a much higher mass or frequency range compared to all other experiments like ADMX. So this is a typical exclusion plot where we have mass on the x-axis and the G gamma gamma on the y-axis. Over the past few years, we published a few papers excluding axions in this challenging region and improving our axions. So these are the main results from our group. And the latest advancement in the development is called Organ Q. Q stands for quantum, and we are trying to leverage low noise quantum limited amplification, in our case in the form of just symptomatic amplifiers, which we can implement into our setup. This is all microwave stuff, coupled to classical Sikivie haloscope. This is what we are running right now. So on this plot, you can see that we managed to design our cavities with a very clean spectrum, because if we have interaction with other modes, typically you will get lots of points where you lose sensitivity. In our case, it's very nice, and we keep put bounds on axions in the higher mass. So we are here, and we are higher than anyone else in the field. At some point, we asked the question whether it is necessary to use the DC field for the experiments, and the answer is no. And in principle, both E and D in this interaction between axions and the electromagnetism would belong to oscillating fields. And with this in mind, we try to design a cavity where we have these configurations of the field. So E field 1 comes from mode 1, and B field comes from the mode 2, and they interact, they align, so creating non-zero E dot B, coupling us naturally to the axion fields. If we go through the quantization of this experiment, we will end up with a description, quantum optics-like description looking like this, where we have basically two cases: axion upconversion, where the sense for low mass axions in the form of the omega 2 minus omega 1, where these are the resonant frequencies, and the other one is down conversion. And unlike in the traditional experiment where we are looking for thermal noise, for excess over thermal noise, here we are looking for frequency deviation. So basically what we are proposing to do in this work is to implement a clock or feedback oscillator based on two modes with this configuration. And what we are looking for is frequency deviation of these two clocks, which is basically controlled by the axion field. With this in mind, we are limited not by the thermal noise, but by all other imperfections. These clocks are basically the clock stability. And this was our exclusion. And since we are not fighting the thermal noise, we can potentially put bounds even in the tabletop room temperature experiment. And with cryogenics, 4 to 7 Kelvin, we can do even better. So this was our original prediction, and this was our first realization. First of all, this approach has certain advantages. It doesn't need magnetic fields. It doesn't need sophisticated superconductors. We can rely on semiconductor technology. It doesn't need very high powers dissipated. As I said, it only needs 4 Kelvin. No need for sophisticated dilution fridges. And yeah, it's a truly tabletop experiment. So the room temperature looks like this. So this is the whole experiment. This is the cavity in the center, and a single student would put some bounds, although they were not as good as CAS, but still some bounds on the axion fields. So this was done in a couple of days' work. So the main, was the prototype, of course, and the main takeaway from this experiment was that it is relatively hard to design a cavity with two frequencies very close in frequency if we are looking for low mass axions. And what we realized later is that E and B doesn't need to belong to different microwave fields. They can belong to the same mode. So with this in mind, we designed a cavity which has this property non-zero E dot B, and in optics, this is called helicity. So a mode which possesses this property over some volume would be helical. And we, in this work here, we demonstrated that we can design a cavity with relatively large helicity. And our solution was to implement either triangular or square resonator and twist it. And this twist is what creates coupling between E dot B and naturally couples everything to the axions. So in this cavity, this is linear one, this is kind of Möbius-like one. We have non-zero E dot B, and we can naturally, with a single mode, couple to axion fields. And since we need only one, we could put, this is a much easier design, and we can put very stringent bounds on axions, given that we can achieve very high quality factors. Shifting gears a little bit, later in quite recently, people realized or rediscovered this effect, which is basically the idea that electromagnetism is coupled to the gravity effects, and that if you have a microwave cavity or an optical cavity, you can a gravitational wave can deposit some energy in this cavity. And this was discussed in the literature. These are works of our colleagues who argued that you can, in principle, either use data from axion experiments like Oregon or ADMX or Haystack to bounds on high-frequency gravitation waves. So this is the kind of hot topic in the field. And with this in mind, I want to shift gears to acoustic cavities or devices which look like this. And the idea here is that in acoustics, we have an absolute analog of the well-known Fabry-Perot cavity. Fabry-Perot cavity is the cavity where light bounds between two mirrors, creating a standing wave. Here we have a standing waves of phonons bouncing off two mirrors, and mirrors are basically interfaces between a solid In our case, it's pores and vacuum. So despite gaps here are vacuum. And we also use like use convex approach, and basically we uncouple our wave, which is concentrated in the center, from the clamping points, and this increases our Q. So the devices themselves look like this. So this is a well-established technology. Again, we use clocks and space exploration. Typical frequencies are in the range of 1 to 1 megahertz, 1 gigahertz. We have two transverse wave, and unlike in optics, we have one longitudinal wave. We have piezoelectric coupling, so we don't need sophisticated parametric systems to couple with mechanical vibration. This is a well-established technology. Its quality factors are basically at 4 Kelvin or millikelvin. They approach 10 billion, which is extraordinary. And there are plenty of those modes scattered in this frequency range, with masses ranging from gram to milligram. And what we realized later is these are absolutely analog also to old school bar detectors from 1990s. So this is how they look like there. So these are devices used to detect low frequency gravitational waves at hertz scale. So these are bars of niobium in this case. And our devices basically very similar in geometry. They're just skinnier. And the main difference is we are looking for much higher frequencies here, 10 to the 6, 10 to the 9 hertz. Advantages, we can cool it even further. This was called 4 Kelvin, we could cool to 20 millikelvin. We have hundreds of modes in this range. We have excellent quality factors, and we can naturally couple to squids. And this is an easier experiment than this one. So in this paper, we calculated strain sensitivity of all modes in these devices, and we achieved quite an impressive number. So this is 10 to the minus 22, and this is not very far from LIGO actually, but we are in a much higher frequency range. So we are talking about hundreds of megahertz all around. And the experiment will look like this. So gravity wave comes to this plate, excite vibration, and we detect the wire, a squid, a superconducting amplifier as an excess over thermal noise. So these are actual measurements. So this is thermal noise in one of our devices, which we can monitor in time and search for high frequency gravity waves. And the first question people ask about this experiment is, are there any sources? And this question we tried to answer in this paper. So this is a huge collaboration between people, theorists and experimentalists, shooting ideas about experiments and theories. And basically in this paper was the first unified proposal on sources as well as experiments. So bulk acoustic wave is our experiments, and in some cases we can cover some range and we can achieve some results. And the uniqueness of our experiment is that at that point it was the only one which was actually running. And yes, there are sources answering my question, and the caveat here is that all of them describe new physics. So this is beyond the standard model physics candidates. And the one we will discuss later are called primordial black holes. So we run our experiment for 153 days, and this is our first results. And over these 153 days and two modes in a single detector, where we managed to detect 2 or 3 events, and they look real, so they do belong to the cavity itself. So this is not external. We tried to correlate it with some other observations around, and we couldn't match it with anything. With this in mind, we are trying to improve our experiments. We call it MAGE, multi-acoustic gravitational wave experiments. In this case, we have 2 antennas, so 2 independent squids, 2 independent ports, resonators. We have improved our digitization. Now instead of 2 modes per antenna, we have up to 16. We have much more channels. We are trying to implement veto as well in the form of cosmic ray detector sitting underneath this experiment. So this was one of our explanations, that these vibrations are caused by high energy cosmic rays. The other two explanations was that this is due to stress relaxations and radioactive events. In any case, having two independent antennas will help us to decorrelate the events. The other feature is this muon detector, which is coming online. So again, this is quite an advantage over the first experiment, and these are the first results. So this on the left, we have the histogram. So these are the events, and these fitted lines here and here, these are basically the thermal noise limit, which we can estimate from our knowledge of the antenna. And this tail here is the excess of those extra high energy events which we observe in our antennas. Comparing two antennas together, we realize that all of them, except for one, are uncorrelated. So they are caused by one of the three causes which I described earlier, even without the beta detector. But yes, there is one which we believe could be correlated between the two antennas. In any case, with this data in mind, we're trying to put bounds on primordial black hole mergers. So this is the main result. So the green block here is our bounds on, I believe this is on the order of 50 days running. And this is what we observe. And we can compare this to other people doing LIGO analysis in this region. And yeah, we can exclude primordial black holes to some degree. And this is becoming astrophysically irrelevant as we are kind of going at this point, we're reaching the extent of the galaxy. So we are reaching the Voyager 1. It's not like ridiculously small arrays around our experiment. And with the next step, which is going to millikelvin, this dot here, we will be able to extend this even further by quite a few orders of magnitude, actually. So this will be here. But these are still all the preliminary results. Switching gears to dark matter again, people used our results and our proposals to understand whether they can use such devices to put bounds on ultra-low mass dark matter. And these are the examples of two works from our colleagues who said basically some candidates of dark matter can modify the Bohr radius with this. They excite vibrations in chemical oscillators like ours, and they can recalculate, they can take our strain sensitivity and recalculate into the limits onto dark matter coupling. So these D coefficients, the coupling to certain candidates for dark matter, and they can use our data to put bounds as well. So this is quartz bound acoustic waves here and quartz here. So basically the takeaway here is acoustic cavities, multi-acoustic cavity devices can be used to detect dark matter in addition to high-frequency gravitational waves. Which brings us to the idea of comparing dark matter and gravitational wave instruments, and this is what we discuss in this paper here. And the main plot is this. Basically, the idea here is we can bring everything in a source-independent way to strain sensitivity. So this is a square root of strain sensitivity in the units of 1/square hertz, and we can put bound experiments like LIGO and MAGE from the gravity wave detection schemes together with ADMX and organ together in the same axis, and this is the frequency range, so it's strain sensitivity, and we can see that organ and ADMX are not that far from LIGO, so that in principle these instruments are comparable. And the main takeaway is that this offers a new way to have dual purpose detection where we can target both dark matter and gravitational wave, high frequency gravitational waves as well. So with this, I want to conclude. I want to highlight the group. So we have quite a few students working on different aspects of this experiments, and the group, the most probably known person in the field is Mike Tobar, who is the leader of the group. So with this, I want to conclude, and I'll be happy to answer your questions later. Thank you.